Okay, our next topic is called chemical bonds, and we're only going to talk about 3 types of chemical bonds in this particular tutorial lesson: ionic, metallic, and covalent. And we define a chemical bond as a force of attraction that holds 2 atoms together. They are chemically combined. They are not physically combined, they are chemically combined. So let's ask ourselves one question: why do atoms want to form bonds, right? And there's got to be a driving force or a reason for atoms to form chemical bonds, and it's quite simple. The atoms want to form bonds to become more stable. And in general, this means to achieve the octet rule, where atoms are most stable when they have a full valence shell of electrons. And in other words, they achieve a noble gas configuration, right? And the only 2 elements on the periodic table that do not have this octet rule apply to them are hydrogen and helium. That's because they only have a maximum of 2 valence electrons in their 1s orbital, and therefore they don't necessarily achieve the octet rule, but they do want to have a filled valence shell which includes 2 electrons. Now, to achieve a chemical bond, atoms will either gain, lose, or share electrons so they can complete their valence shell. And that's how they form chemical bonds, by gaining, losing, or sharing electrons to complete their shell. Okay, so let's talk about bonding and potential energy with respect to bond energies. Energy is released when a bond is formed, okay? So energy is released when the bond is formed, and that is a exothermic process because we are releasing energy. And we must absorb energy in order to break a bond. So there's a bond in existence. We need to overcome the forces of attraction to break that bond, right? And the stronger the bond, the more energy is involved to break it. And the energy required to break a bond between 2 atoms is known as the bond dissociation energy. So the takeaway from this slide is that there's potential energy stored in chemical bonds. Our first type of bond that we're talking about in this tutorial is an ionic bond. And ionic bonds are formed through a transfer of electrons from one atom to another. And therefore we are forming ions. And a positive ion is a cation, and a negative ion are formed and then are held together by electrostatic forces. So basically they're opposite charges, they attract each other. And ionic bonds are only formed between metal and non-metal elements, and only when there is a large difference in the electronegativity, right? So the electronegativity, remember back from the periodic table, we talked about the electronegativity being an atom's ability to attract or acquire electrons, and the higher the number, that means that the more an atom wanted electrons. So, for example, let's just do a quick example here. Chlorine has an electronegativity number of about 3, and then sodium has one about 0.8. And the difference between the two is 2.2, which is much greater than 1.5, and therefore sodium chloride would form an ionic bond based on this rule. And remember that when we form bonds, the metals will lose electrons and to try to reach their noble gas configuration, and the nonmetals will gain electrons to try to reach their noble gas configuration. And then when we hold the 2 together, we call them salts. All right, so they're salts. And the salts are the common name for any type of ionic compound, right? Magnesium oxide is a salt, sodium chloride is a salt, cesium fluoride is a salt, sodium fluoride is a salt, copper fluoride is a salt, anything like that is a salt. Okay, so let's look at this from a closer standpoint as far as electrons. So we look at sodium and chlorine, and we're just going to first we're going to look at which are the valence electrons for sodium. The valence electrons for sodium are only the 3s electrons, right? There's only one of those. And then the valence electrons for chlorine are going to be the 3s2, 3p5. So there's going to be 7 here, and then there's going to be 1 here. So both together they add up to 8, right? And so what's going to happen is this electron here is going to be the sodium electron is going to be donated over to the chlorine, and therefore we're going to be left with a sodium plus here, and then a chlorine minus here, right? And therefore when we do that, we're now going to back to the configuration of a full octet here, and notice that this was the one over here that was already full, and now our new octet here is full because I've acquired 1 electron from the sodium atom. So now this octet is full, and therefore these two will get together and form a chemical bond from the electrostatic attraction forces, right? Okay, so now let's look at ionic bonding in relation to oxidation numbers. Now, if you remember back to the periodic table and some other earlier chapters, we talked about oxidation numbers, and here's where they come into play. Remember, all metals will lose all of their valence electrons to form a cation, right? And let's look at calcium, for example. Calcium has 2 valence electrons. It's going to lose both of those, and therefore we're going to get this +2 thing. And remember, calcium has a +2 oxidation number. So if you remember back on our periodic table, we assigned that the alkali metals were +1 oxidation, alkali earth metals, which was calcium, was +2, aluminum boron, that was +3, etc., etc. And then the oxidation number for things like chlorine was -1, oxygen -2. So now let's go on that one. And now we have nonmetals will gain as many valence electrons as they need to be full. And for example, for chlorine, again, it can get 1 more electron in this spot here, so it will try to find one, and when it does, it becomes negative, right? And here's that, and therefore it's now become the fluoride ion. And remember, the fluoride ion, or the oxidation number for fluorine, is -1 because it only needs 1 electron, right? So it's -1. It's going to get a 1 electron, which will make it more negative. And this one has 2 electrons to give away, so that's why it's giving them away. It's plus. Okay, so you have to remember that even though ionic compounds are made up of ions, right, which are held together by electrostatic forces, the overall net charge on the compound is neutral, right? Because the total charge of the cations is going to be equal to the total charge of the anions. And we adjust the ratio of the positive ions to the negative ions to make sure that we can balance the charge. And then the lowest ratio is referred to as its formula unit, right? So we have formula unit for sodium chloride is NaCl, and magnesium chloride is MaGCl2. Now let's remember back how we did that. For those of you who can't remember how we did it. So we know that magnesium, for example, has a 2+ charge, right? That's our oxidation number. It wants to lose 2 electrons, so when it does to lose 2 electrons, it gets the 2+. And we know that chlorine is -1, right? So it's 1-. And because it wants to gain an electron to get to a full octet. And then to make the formula, remember we drop all the plus and minus, and we just take the superscripts, of the charges, and then we make them subscripts on the opposite side, so we cross multiply, and then we get MgCl2, right? And we drop the plus and minus, and remember we don't write the coefficient of 1, the subscript of 1, we just leave it as is because it's already assumed, right? So that's how we get the formula from the ionic compounds, from the total charge of the anions and cations. Okay, here are some more examples. I'm going to go through these relatively quickly. Remember that here's calcium and oxygen, and remember that calcium is a 2+ oxidation number, right? So that's the 2+, and then the oxygen is always 2-. And if you do the crisscross rule here like this, you'll get calcium 2, oxygen 2, but we know that we can further reduce that to be calcium oxide, right? Because you could divide each one of these sides by 2, and you're having to change the charge on it because you're dividing each one by 2. And now look at something with imbalance of charges, right? Remember potassium and sulfur, +1 for potassium and -2 for sulfur. So we need 2 potassiums to balance out the sulfur. And so our final formula for this would be Ks2, and the vice versa for the bottom one here. We need 2 -1s from the bromine to balance out the +2 from the barium, so we'd have bromine 2. And that's how that works. Right, so those are just some examples, and this shows you where the electrons are coming from on this side of the sheet of the slide. Okay, ionic solids have some pretty unique properties. First of all, they all form crystalline solids, right? So they all form crystalline solids. And the crystal shapes are defined by a variety of things. One is how the orbital overlap is, the ratio and size of the 2 ions. And in general, most of them are either face-centered cubic, body-centered cubic, or hexagonal close packed for a majority of the salts involved. And they have high boiling points and high melting points, right? They don't boil low or anything like that. And they're very brittle. So when you put a stress onto let's say you put a stress onto an ionic solid, it cleaves cleanly across the interface where there have the ions are next to each other. So, for example, chlorine and a sodium ion and sodium chloride, that's where the bond is going to break, right? It's not going to break along, and it's going to break along that surface along all of them, right? So you're going to have a chlorine, you're going to break here, you're going to break here, break here, and break here. And typical the stress strain curve for a brittle solid, like an ionic solid, will look like this. And this is our stress, and here's our strain, that's E. And then what will happen is you'll have a very, very, very high stress, and then it'll just fracture real quick, and it's broken. Whereas a ductile solid, or something that's a little bit less brittle, is going to be more like this. You'll get some yielding involved, and then it'll break somewhere down here. So that would be like a ductile plastic or something like that. All right, and then the final thing you have to understand is that the materials will conduct electricity in the molten phase or the liquid phase. So a liquid sodium chloride will be very conductive, or when they're dissolved in water due to the freely moving ions. But in general, as a solid, as ionic solid, they are not very conductive of electricity. Okay, our next type of bonding is metallic bonding, and metallic bonding only occurs in metals, right? And since most metals have 1 or 2 valence electrons, and they also have low ionization energies, in other words, energy associated with removing the electron from the outer shell, you can think of metals as like a positive ion, a positive nucleus, surrounded by C, or freely moving delocalized electrons. In other words, a sea of mobile electrons. And what I mean by that is, I've drawn a series of copper atoms here, and the blue line represents the electron cloud around each one of the copper nucleuses. And then I've given you a visual for the 1 valence electrons for copper +1, right? And then, so what happens, what I mean by the sea of mobile electrons is that this electron here can move over to here, and this electron could just as easily move back here because they're so loosely bound and they're so delocalized that they can randomly move around in this this sea of mobile electrons, and it's just as easy that this one can move here and this one can move here, or this one could move down here or here, because they're all overlapped in this whole big sea, and because of this constant motion back and forth, they are very good conductors of both electricity and heat. All right, and you know, they're not really going anywhere specific, but they're not moving, or they're not causing a current flow, as would be for electrical flow. But they are constantly moving around in this big giant cloud of electrons because they're so loosely, they have such a low ionization energy, and they're so delocalized. And the last thing to remember about this, about metallic bonding, is where we form alloys, right? So an alloy is just a mixture of metals. Examples are brass, bronze, and steel. And remember back to our description of a mixture, there's two types. There's heterogeneous and homogeneous, and an alloy is a homogeneous mixture, or in other words, it's also called a solid solution. Okay, so from the previous page, we do know that for one of the properties of metals, they are good conductors of heat and electricity due to that sea of mobile electrons, and that can move freely around. They're ductile and malleable. In other words, they can be shaped and formed easily. They have high luster, and it means they're shiny. And if you cut a piece of a metal, it's usually the cut edge is very, very shiny. Over time, some of them will oxidize and tarnish. That's because of the chemical reaction going on. But if you fresh cut, it's going to be very, very shiny, very, very metallically looking. And they have a variety of melting and boiling points. And I'll give you one example. It's a very low melting boiling point is mercury, which is one of the very few liquids in the periodic table. And yet it's a very heavy metal. Okay, our last bond is covalent bonds, and covalent bonds are formed by atoms sharing electrons. Right, they have to sharing electrons, and that's the key to this, is the sharing of electrons for a covalent bond. Think of covalent bonds are atoms that are co-owners of valence electrons, and the prefix co means jointly or join, so they're jointly owned by both atoms. And they form between two nonmetals, right? So that's another key thing here. They form between two nonmetals. And compounds that are formed with covalent bonds are called molecular compounds, and the covalent bonds are called molecules, right? So molecules are formed from covalent bonds, and compounds that are formed with covalent bonds are called molecular compounds. Each bond consists of a pair, which is two electrons, of shared electrons, and we represent that in a bonding situation with a dash. Right? So here's a dash down here representing a sharing of electrons or a covalent bond. And then atoms will form as many bonds as they need to fill their valence shell. Now, there are some exceptions to this, or there are some rules to this, and we'll talk about that in a few seconds. For moving forward, a single bond is one pair of shared electrons. A double bond consists of two paired shared electrons, and it's represented by the double lines. And then the last one is our triple bond, right? And our triple bond is our three pairs of electrons, and that's going to represent that there, all right? And the last thing to do is you're going to ask, well, why can we not have a quadruple bond? And you can have quadruple bonds, but you do need to have at least a d orbital involved, because you need to have additional areas for the bonding to occur. And remember, each orbital is involved in bonding. So when you have an s and a p orbital, you can only have a maximum of 3 bonds in that, right? Because there's a hybridization of the orbitals, is sp3, and that we'll talk a little bit more about that in another tutorial. But for the most part, unless you have a d orbital, you're not going to be able to form a quadruple bond. And even so, they're very rare in nature. Okay, so let's look at the simplest form of a covalent bond involving two hydrogen atoms. And so we're going to have hydrogen atom 1 here, and we can see that it has only one electron right here. And then we're going to have hydrogen atom 2, and we're going to have one electron here. Now, in order to form a bond, we need to do a sharing of two electrons, right? So electron from this electron is going to be shared over here with this hydrogen atom. And this electron here is going to be shared with this hydrogen atom. And then our final bond is going to be the sharing of these two. So those are the two electrons that are going to be shared, and we would represent that by H, solid line H. And here is just a more elegant way of drawing that. Okay, so let's look at the covalent bond based on electron density around each individual atom that brings electrons to the bond. And so this is our simplest one, which is our hydrogen atom, remember. So back before, we just showed that the electrons were 2 points, and when they're really not, remember, they're the big densities of these, the probabilities of finding energy around a nucleus. And so here's our this is our two atoms here. So we bring them in, they look like this, right? The two 1s orbitals, which has one electron each. And then we overlap them as they get together. And you can see here is where the actual the bond is going to be start to form. And then when we do that, we make a hybrid orbital now, an hybrid s orbital with the two orbitals, s1s orbitals coming to play. And then that's represented by this here. So the maximum density is around this area in here, and which is represented by this area in here. And then you see a little bit of less density out here, and which is represented by the lesser darkness here, or the lesser lightness there. Okay, our last slide of the thing is properties of the molecules that are made up from covalent bonds. So we're going to put covalent here. And we know that for covalent bonds that they're shared electrons, so they're going to have a little bit different properties than our ionic or metallic bonding materials. So for our visual, we're going to think of candle wax, which is a low molecular weight hydrocarbon. And the phase, solid, liquid, or gas, depends on the forces of attraction between the molecules, right? So things like oxygen and nitrogen, which have really no forces of attraction between the molecules, have very low melting points and boiling points, right? They're in the 100 degrees Kelvin range, which is quite low. And then for things like water, which is H2O, which is a covalent compound, but does have strong intermolecular forces, not intermolecular forces. They are going to be, it's going to boil and melt quite high compared to its molecular weight because of all the hydrogen bonding that goes on. And we're going to talk about hydrogen bonding a little bit later. Typically, if it's a solid material, it's going to be soft and not brittle, and you can think of, again, the candle wax application. And they're poor conductors of heat and electricity. Again, think about the candle wax. And in general, they have low and melting and boiling points. However, some materials that are covalently bonded have extremely high melting and boiling points, and they are covalent solids. And I've worked with two of them. One of them being silicon carbide, and let's just write that down as a compound, silicon carbide, and the other one was silicon nitride. And both of these are covalent solids, and both have covalent bonds throughout them. There's no ionic bonds, but they do have crystal structures and do require high bond energies in order for them to break down. And therefore, silicon carbide starts to decompose around 2900 degrees C, and silicon carbide roughly 2700 degrees C, which is quite hot compared to your normal methane or propane or butane, or even your candle wax, or even your plastic container that you cook your food in, your Tupperware stuff. So not always is the case that you have low melting and boiling points, but in general, the trend is that if it's a covalent solid, a covalent material, it's going to have lower melting and boiling points compared to, let's say, the ionic solids.